I'm Mark Cavanaugh for Cavi Coaches, and today I'm going to coach you up on the Great Race. So what is the Great Race? So I have four objects that we're going to race down the ramp. I have a hoop, I have a cylinder, I have a sphere, and I have a car. The car is mostly translational motion, where the other three are in rotational motion. So I'm going to give you a second to think about which object, if any, will reach the bottom first, and see if you can come up with an explanation for why. Okay, hopefully you had enough time to think about it. So let's go ahead and run the Great Race. On this slide that we're going to look at the kinetic energy of each individual particle along something that's rotating. So we sum up all the individual masses and individual velocities, and we use the equation k equals 1/2 mv squared. Now each object does not have the same speed, so we're going to change the speed into the angular speed multiplied by the radius. So we can see that we end up with the 1/2 of mi times omega times Ri, in that quantity. Change this equation, we end up with 1/2 mi Ri squared times omega, and the sum of the individual masses times individual radius squared, that is the rotational inertia. So we end up with 1/2 the rotational inertia times the angular velocity squared. And because each particle does not have the same velocity, therefore it has the same angular speed. Now, if we look at this slide, this is looking at what it means to have an object rolling without slipping. So we have the translational motion is going to be the same, whether it's the center of the mass, the top of the sphere, the bottom of the sphere. Now, if we look at the rotational speed, at the top, the rotational speed is towards the right, and at the bottom, it is towards the left. Now, if we look at the sum of all of those, we can see that the top is going to be moving twice as fast as the center of mass, and the bottom is not moving at all. So what this shows us is this is what is the definition of rolling without slipping, where we have static friction between the bottom of the sphere and the ground. The same thing works with your tires on your car. So what that means is when we compare the effects of the rotational inertia and its distribution of kinetic energy, the total kinetic energy is going to equal the rotational kinetic energy plus the kinetic energy of the center of mass. So the greater the I, the greater the rotational kinetic energy, which means the bigger the rotational inertia. We're starting to explain what's going on here with the Great Race and why the results were what they were. So we look at the Great Race. We know that the particle finished first, then the sphere, then the cylinder, and the hoop. And we're going to rank those according to their speeds. So obviously, having the same delta x, the same change in position, the lesser time it takes to get down there, the greater the speed. So we're going to calculate the speeds. We're going to use an energy bar chart and conservation of energy equation to do that. So we know the faster the object moves, the quicker it's going to reach the bottom. So we're going to look at the particle first. So if we look at a bar chart, we have the particle in the Earth as the system. It has UG, the same amount of UG for each object to start with. The Earth transfers energy to the particle, and that particle has all translational kinetic energy at the end. So that means UG is equal to K. Translational, we substitute the equations, mgh equals 1/2 mv squared, and we solve for v, and we get the square root of 2gh. Looking at the hoop now, we have the hoop in the Earth as the system. It has the same gravitational energy. The hoop gets its energy from the Earth, but this time the hoop also is rotating along with moving translationally. So it has translational energy and rotational kinetic energy that have to total up to equal the gravitational energy. So UG equals K translational plus K rotational. Substituting the equations in, mgh equals 1/2 mv squared plus 1/2 I omega squared, but that doesn't help us, the I omega squared. So we're going to substitute the equations for the rotational inertia of a hoop, which is mr squared. So I is equal to mr squared. We're also going to substitute in the angular speed as the translational speed divided by the radius. Now, when we simplify this, we can see that the radius cancels out. We've got r squared over r squared, and all the masses are going to cancel out as well, simplifying it down to gh equals 1/2 v squared plus 1/2 v squared, which is just going to be v squared, which gives us v is equal to the square root of gh. So if we compare those, the particle or the car and the hoop, we see that the velocity of the car is equal to the square root of 2gh, and the speed of the hoop is equal to the square root of gh. The car has a greater velocity than the hoop, considering that g and h are the same. Therefore, the car reaches the bottom first, since it's almost completely moving with translational motion. I say completely because the tires are rotating, but the tires' mass are so small in comparison to the car in these particular lab carts that the rotational kinetic energy is basically zero. So with the hoop, it has both translational and rotational motion at the bottom. So therefore, the hoop having rotational motion means that the translational motion cannot be as great as the car. So it's your turn. So what we're going to do is, using the rotational value, inertia values for the sphere, I equals 2/5 mr squared, and the rotational inertia of the disc or the cylinder, which is I equals 1/2 mr squared, what you're going to do is you're going to calculate the speeds of each of the objects at the bottom of the ramp and explain the results of the Great Race. So go ahead here and pause the video and calculate the expression for the speeds in terms of g and h, so you can find the value of each of the speeds. So here we are coming back, the results of the Great Race. So we got the velocity of the car in a previous slide. The sphere is square root of 10/7 gh. The cylinder is the square root of 4/3 gh, and we had the hoop before, the square root of gh. So looking at the coefficients, we know that 2 is greater than 10/7, which is greater than 4/3, which is greater than 1. So therefore, the result of the Great Race gives us the car, the sphere, the cylinder, and the hoop, which also happens to be the reverse order of the rotational inertia. So this explains that the larger the rotational inertia, the smaller the value of the translational motion, because there's a larger rotational kinetic energy. So if we look at the particle sliding without friction, we want to rank them based on which reached the bottom first. We know that's based on the energy. We looked at the energy bar charts. So rolling without slipping provides more rotational kinetic energy. So the greater the rotational inertia value, the greater rotational kinetic energy, which means the smaller the translational kinetic energy. Which one's going to have the greater acceleration? Well, acceleration is going to be based on the change in velocity over the change in time. We know that the particle had the greatest speed and had the shortest time to get to the bottom. The sphere second, then the cylinder, then the hoop. So we know that it's going to be the particle, sphere, cylinder, and hoop, because the biggest change in velocity in the least amount of time. So the question is, which of these is going to go higher? We're going to consider both objects, a sphere that's rolling without slipping and the box slides without friction. Both objects have the same translational speed. Which object will go higher? So let's look at a energy bar chart for the box first. So it has translational kinetic energy to begin with, and the box loses that energy to the earth as it slides up the hill. So we end up with UG. All the box's translational kinetic energy becomes gravitational energy. So now let's look at the sphere. It has the same translational kinetic energy, but it also has rotational kinetic energy. So we can see here that overall, the sphere has more energy because it's rotating and moving the same speed. So that means it has the same translational kinetic energy. So as it rolls up the ramp, the sphere gives the energy to the earth, and it's going to slow down rolling as well. So at the top, it's not going to be rolling or moving translationally, so it's going to be all gravitational. you can see the gravitational energy here is much larger than the energy before, and that's because it has the sphere has the same translational energy, but also has rotational. What that means is the sphere has more overall energy than the box, so its rotational energy is going to end up taking it higher up the ramp. So this is a quick video showing you the values of rotational energy and how you can use bar charts and objects and why objects will not end up at this bottom at the same time based on the larger rotational inertia. I hope that this is helpful, and I'll see you next time on Cavi. If you found this video helpful, don't forget to click the like button down below and subscribe to my channel, Cavi Coaches, and follow me on Instagram and Twitter at Cavi Coaches.